In 2026, a machine did something humans could not do for 80 years. An AI reasoning model produced a complete proof that disproved a famous old conjecture in geometry. Mathematicians checked the proof carefully, and it held up. For the first time, an AI had cracked a real open problem at the very frontier of mathematics. To understand what happened, let's start with the puzzle. Imagine scattering some dots on a flat sheet of paper. Now pick a distance and call it 1 unit. The question is simple to ask. How many pairs of dots can be exactly 1 unit apart? Some pairs will be too close, others too far. Only certain pairs land at exactly the right gap. This question was first asked back in 1946 by a mathematician named Paul Erdős. Erdős loved problems that sounded almost childishly simple, but hid enormous depth. This was one of them. It became known as the unit distance problem. And for decade after decade, it refused to give up its secrets. Here is the heart of it. As you add more dots, the number of unit distance pairs can grow. The real question is not just how many pairs you can get. It is how fast that count can grow as the number of dots gets large. Mathematicians call the number of dots n. They wanted to know the fastest possible growth in pairs as n climbs higher and higher. So, what is the best way to pack in those pairs? The natural answer is a grid. Line your dots up in neat rows and columns, like graph paper. Set the spacing to exactly 1 unit. Suddenly, every dot has neighbors above, below, left, and right, all exactly 1 unit away. A grid creates a huge number of unit distance pairs at once, far more than a random scatter of the same dots. For a long time, the grid looked unbeatable. So Erdős made a bold guess. He conjectured that the grid is essentially the best you can ever do. In his belief, no clever arrangement could push the number of pairs much higher. The count would grow only barely faster than n itself. That guess became the famous Erdős conjecture, and it stood for generations. Now, nobody could prove Erdős's guess was right. But in 1984, 3 mathematicians, Spencer, Semiretti, and Trotter, proved a hard ceiling. They showed the number of pairs can never exceed about n to the 4/3 power. That is the absolute maximum, no matter how you arrange the dots. But here was the problem. Nobody could prove the true answer was actually much lower than that ceiling. So picture 2 lines. Down low, the grid, growing barely faster than n. Up high, the proven ceiling at about n to the 4/3. Between them sat a wide gap of pure mystery. And for 40 years after 1984, that gap stayed completely frozen. Mathematicians pushed from both sides. The grid would not climb higher, and the ceiling would not drop lower. Nothing moved. Then came the AI. OpenAI's reasoning model went looking for a better arrangement of points, and it found one. Not a tidy grid, but a strange, irregular cloud of dots, built using special numbers called algebraic numbers. It looked nothing like graph paper, but it packed in more unit distance pairs than the grid ever could. The AI had discovered an arrangement that beat the supposed champion. This was not a small improvement. The AI's arrangement beat the grid by a fixed, non-shrinking amount, even as the number of dots grew huge. And that mattered enormously. Because Erdős had said the grid was near the best possible. If something can clearly and permanently beat the grid, then the grid is not near optimal at all. In one stroke, the AI disproved Erdős's 80-year-old conjecture. Soon after, a mathematician named Sawin dug into the AI's proof. He extracted a concrete number from it. He showed the true count grows at least as fast as n to roughly the 1.03 power. That is, comfortably above the grid. It pushed the lower bound up for the first time in decades. The gap to the ceiling at about n to the 4/3 got smaller, but it did not close. Now, why would an AI be good at this kind of task? Here is a clue. Disproving a conjecture only needs one clever counterexample, just one arrangement that breaks the rule. That suits a machine perfectly. An AI can search through countless possibilities, tireless and patient, until it finds the rare one that works. But it does not stop there. The proof still had to be read, checked, and verified by human mathematicians before anyone trusted it. This is why the moment feels so significant. The AI did not just crunch numbers faster, it found a genuinely new mathematical construction, an idea humans had missed for 80 years. In fact, a human mathematician had once tried this very style of approach. It usually fails, so he gave it up. The AI did not give up. It kept searching the space humans had quietly abandoned, and there it found the answer. But let's be honest and precise. The unit distance problem is not solved. Far from it. The exact growth rate is still unknown. We now know the answer sits somewhere above n to the 1.03 power and below n to the 4/3 power. That is still a wide gap. So the right way to say it is this. The AI disproved a famous conjecture and improved the lower bound. It did not close the problem. And this is not a one-off. It is part of a wider wave. Across 2025 and into 2026, AI systems have started to contribute real new results at the frontier of mathematics. Not just rephrasing what humans already knew, but finding things that were genuinely missing. The Erdős disproof is one of the brightest moments in that story so far, and it likely will not be the last. So here is the lesson worth remembering. An AI found something humans had missed for 80 years. Not by being smarter in some magical way, but by searching tirelessly through a space of ideas that people had quietly given up on. The dots we started with looked simple. The answer was anything but, and the search for it is far from over.